Welcome to the E-Pathshala lecture series on computer science for postgraduate students. We are learning the subject computer graphics and visualization. In this series, we had done few sessions earlier. So, this is the fourth session in this series. In this session, we will take an example of Bresenham's line drawing algorithm, and with that we will see how Bresenham's line drawing algorithm is advantageous with a problem, and later we will look at the midpoint circle drawing procedure, which is an important procedure as part of this primitives. So, if you recollect the discussion, we started with introduction in the first session. We had learned some definitions and basic terminology, and later in the second session we had talked about the DDA line drawing procedure, and in the third session the Bresenham's line drawing procedure, and today now we will solve a simple problem based on Bresenham's line drawing procedure, and later we will continue with the midpoint circle drawing procedure. So, let us take an example problem to understand from deep how Bresenham's line drawing algorithm works and is more superior to the DDA line drawing procedure. So, let us take an example. If you recollect the discussion, for lines m less than 1, that is slope less than 1, and m is positive, we will be sampling the line along x axis at unit intervals. Let us take the problem. Given two endpoints of a line, x is equal to x k plus 1, next y is equal to y k. So, the next pixel to be plotted is x k plus 1 comma y k. So, the next decision parameter correspondingly is p k plus 2 delta y. If you write these equations by the side and keep doing the calculations, you will understand this better. So, we started with k is equal to 0 and p k is minus 2. So, choose that is 3 is the next x and 2 is the next y, which is same as previous y, that is 2 2 2. For the next decision parameter, which is p1, so compute p1 using the equation P0 plus 2 delta y, because we are in this case. So, P0 plus 2 delta y, that is P0 is nothing but minus 2 plus minus 2 plus 2 into delta y is 3. So, minus 2 plus 6 is 4. So, the next decision parameter P1 is positive. So, P1 is positive means k is equal to 1, P1 is 4. So, because it is positive, the next y is the one higher than the previous y. This is previous y and the next y is 3. So, if you look at this equation for Pk greater than 0, the next y is previous y plus 1. So, if you continue further like this, that is compute the next decision parameter using this equation, because we got a case greater than 0. So, Pk plus 1, which is P2 is equal to P1 plus 2 delta y minus 2 delta x. That is how you should be calculating for the next decision parameter. So, that is called as 2 P2, which is minus 6. When you compute, you will get these values minus 6, and the next x value is 5, but the next y value, because this Pk is negative, same as previous y. And what you should observe is, when we compute points or decision parameters using Bresenham's line drawing procedure, the interesting fact is that the Pk values either are increasing or decreasing, that is either positive or negative or 0. So, that means they are not always negative or always positive or always 0. So, they keep fluctuating about the true theoretical line. So, you should observe that, and you can you will notice that the points accordingly will keep fluctuating. So, when you compute these points till k is equal to 6, that is the last point where x k plus 1 is 9 and y k plus 1 happens to be 5. So, the points to be plotted are 3 2, 4 3, 5 3, 6 4, 7 4, 8 4 and 9 5. So, that is the solution for the first problem, and similarly for m is less than 1, but m is negative. So, that is mod m less than 1, m negative. As I said, for negative slopes, one of the coordinates is increasing while the other coordinates will be decreasing. So, in this case, given 2 comma 8 as the x coordinate and the y coordinate, that is the initial point, the first point, and 10 comma 5 is the next point, that the end point of the line, the two end points of the line. So, if you take del y by del x, this is negative, m is equal to minus 3 by 8. So, x is increasing from 2 to 10 while y is decreasing from 8 to 5. So, the delta y becomes negative. So, do not bother about the m is negative and mod m less than or equal to 1. You still follow the same set of equations, but only the change that you will be doing is wherever there is delta y and delta x, you take modulus of that. Okay. So, the same equations you will be using, but use modulus for delta y and delta x. That is the important observation, and based on that a problem is solved here. You will easily understand when you start doing this. You can sit and start doing this as we did for the in the previous case, previous example. You follow same set of equations, because it is only the modulus, that is m is less, mod m is less than 1 and m is negative. So, only change is that one of the coordinates will be increasing while the other will be decreasing. In this case here y is decreasing. Okay. So, as you see here, x values keep increasing 3, 4, 5, 6, 7, 8, 9 by 1 unit, while y's keep decreasing 8, 7, 7, 6, 6, 6 and 5. So, and you still could observe this, that Pk is actually not fully negative or not fully positive. All the values are, they are actually fluctuating between positive and negative values. So, when you observe now the two algorithms, if you compare with the theoretical line, that is theoretical line is something that you could draw using the exact values, but whereas when we use algorithms like DDA or Bresenham, we get an approximation only. Bresenham gives a better approximation for the theoretical line, and if you observe the shapes carefully, the green line indicates the Bresenham's line, the blue line is the theoretical line, and the red is the DDA line. The red line, DDA line, is actually fluctuating away from the blue line, it is moving away, the gap is getting wider and wider, while the Bresenham line, the green one, is actually going about the theoretical line, that is it fluctuates about the theoretical line. That is the beauty of the Bresenham's line. So, it is more accurate. Okay. So, that is how it is more efficient than the DDA1. So, it also solves the problem of floating point calculations. So, because of these two advantages or fundamental advantages, it is more efficient and also avoids floating point calculations. It is a more better algorithm and is also accurate because it always fluctuates about the theoretical line. So, it never deviates from the theoretical line. That is why you sometimes get positive, that is pk is sometimes positive, pk is sometimes negative. That means our pixels that we choose will be either the upper one or the lower one for every new pixel that we compute. So, with this we come to the end of the Bresenham's line drawing procedure. Take many possible line slopes and try to solve many example problems for positive slopes, for negative slopes, and for horizontal and vertical lines. You would appreciate using the set of equations that are given in the previous slides. So, let us step into the next primitive, and we have started with point, which is just a location in space, then line, which is the next important primitive. The third important primitive that we are going to look at in this session is the circle drawing procedure. So, circles are the most important primitives, are most common primitives that everyone uses. So, a circle is very much symmetric, that is, a circle has got a nice shape, and its important property is that it is symmetric, that is, it exhibits octant symmetry. An octant symmetry, octant is 8. So, oct is 8, octant is 8. So, it exhibits symmetry about its octants. What does that mean? This example here in the slide shows what is this octant symmetry. Suppose you are given a circle, okay, divide that into divide using these lines as the radial lines. Using these lines you can divide the circle into 8 pieces. So, each piece is an octant. Okay. Now, take one of the octants. Okay. You can do all your computation on one of the octants. So, for example, if you had computed a point using any algorithm or using any procedure, if you had computed a point on one of the octants as 2, 7, say for example, this is the octant of our interest, and we have computed a point in this octant as 2, 7. Now, what is the symmetry property? If you know one point, see, in the next octant you do not have to actually compute points, it is just enough you interchange the x's and y's, that is, you will have a symmetric point in the next octant whose coordinates will be just the opposite of the just the swapped versions of the x and y coordinates, which is 7, 2. For this point you can have an exact symmetric point in the other octant, which is 7, -2, actually only a change in the sign of the y coordinate. So, this is 7 and this is -2, this is the symmetric point. For this point, another symmetric point lies in this octant whose coordinates are 2, -7. So, again changing the x and y's and changing the signs, you can easily, and a symmetry is something like you can fold one of the octants about the line of symmetry, and that is how you get. So, another symmetric point can be computed like -2, -7, which is exactly giving an extra sign here for the x coordinate, and like this there are 7 other symmetric points for one point, that is, there are 8 symmetric points, and if you compute one point on one of the octants, the other 7 symmetric points can be easily plotted by interchanging the x's and y's and by giving them signs and changing the signs also. So, that is the interesting part. So, we do not have to compute points on the entire of the circle. It is just enough that we use a procedure, use an algorithm to compute points on only one of the octants, and the remaining 7 points on the remaining 7 octants can be easily plotted by just changing the x's and y's and by interchanging them and by giving them various signs. So, that is as simple as that. For our calculations or for our algorithms and procedures, we will be choosing this octant, that is the first octant, that is the positive octant where x is positive and y is also positive, and the left of these two octants. So, that is the positive quadrant and that in that the left octant. So, given a circle. So, imagine you have to find points on the circle. What is the input? The input to the procedure is the radius, and that is the only thing, and maybe center. So, if center is given somewhere else, so you will have to also take those points or those coordinates. Assume that if center is at origin, so 0 0 is the origin and radius is say some r units, and we will be interested to compute points on the circle only in one of the octants. As I said, it is just enough. We can start with the first point on the octant, which is 0 comma r. So, if r is the radius and if 0 0 is the center, so the first point on this octant that we are considering has the coordinates 0 comma r. So, how do we start our computation, and how do we know where do we stop, or what is the stopping condition for the procedure? Where should we exactly stop so that the quadrant has ended, that is the octant has ended there. So, how do we know the stopping condition, or what is the stopping condition and what is the final point in that octant? That means, this question mark here shows that this is the point that we have to know when we compute we should stop here. So, how do we know that? There are various ways of knowing the stopping condition, and one important, one useful or simplest way to know where we have to stop is, as you know that this is a 45-degree line. Any point on this line is of the form y is equal to x, because it will be 3 3 4 4 5 5 6 6 and 7 7. Any point on this line will be of that form. Any point in this zone, imagine if this 45-degree line divides this quadrant into two parts. Okay. Any point in this zone is will satisfy the relation x is less than y. That means, take any point say 2 comma 5, 2 comma 5 is 2 is less than 5. So, in this octant the points satisfy the relation x is less than y. In this octant the points satisfy the relation x is greater than y, and on this exact line it is x is equal to y. So, we have arrived at our stopping condition logically, saying that as long as x is less than or equal to y, you can continue the procedure, the algorithm can continue computing points. Whenever x is equal to y or x is greater than y, you can stop the procedure. That is, as long as x is less than or equal to y, you can continue computing points on this octant. So, that is how we try to stop the algorithm, or stopping condition for the algorithm. So, that is what is discussed here in this slide as well. And you can also notice that in this octant the slope is actually negative. So, if you start with the circle shape at 0 comma r, here the slope of the circle is actually 0, because the slope to the circle at this point is actually 0. As you keep moving down, x is increasing while y is decreasing. For these points, you see these are all negative slopes. So, in this octant, when we keep moving from left to right, x increases while y decreases. Okay. So, that means, if you observe this octant, the line, the slope of the circle is actually inclined more towards x axis. So, we follow the same arguments that we used for line drawing, where lines with slopes less than or equal to 1, we are going to sample the line along x axis. So, similarly, here for the circle, the slope of the circle in this octant is such that the lines slopes are actually more inclined towards x axis. So, we are going to sample the circle along x axis at unit intervals in this octant. So, if you happen to choose a different octant, obviously you will have to sample the circle along other axis. So, we follow the same logic here. We use the same argument like decision parameter again, and what is our aim is to find a simplest procedure, find some efficient procedure, so that we can compute points on one of the octants efficiently, and the remaining 7 octants, the points can be easily without any computation, we should be able to plot them. So, the circle equation to start with, this procedure is particularly called as midpoint circle drawing procedure. What is a midpoint circle drawing procedure? Is we are going to use the midpoint, and let us see that in the next slide. And the circle with center at origin and with radius r units is given by the equation x squared plus y squared is equal to r squared. So, as we know from coordinate geometry that x squared plus y squared minus r squared, if it is equal to, that means any point x comma y that satisfies this relation is a point that lies on the circle boundary. Any point x comma y, when you substitute that in the relation x squared plus y squared minus r squared, and if it is less than 0, the point is an inside point. So, it lies inside the circle boundary, and any point x comma y that satisfies this relation is an outside point. So, our decision parameter here, that is whether a point is on the circle or is an inside point, is an outside point, we can compute by checking the decision parameter pk. So, if we equate pk to be x squared plus y squared minus r squared, we can say that whenever pk is less than 0, it is an inside point, whenever pk is greater than 0, it is an outside point, whenever pk is equal to 0, it is a point on the boundary. That means, always we have to find a point close to the theoretical position on the circle. So, that point may be an outside point or that point may be an inside point. So, we will be actually trying that. So, for that we use the concept of midpoint. So, what is the midpoint procedure? Let us understand the principle of midpoint circle drawing procedure. We start with a known point on the circle. Always we start with a known point or a plotted point. Let us say it is xk and yk, the point is plotted. So, to compute the next unknown point, we have to decide, or we have to find out what is the next unknown point. For that, because the circle is assumed to be sampled along x axis, the next x value is 1 higher than the previous x value. So, the x position is known. So, the x coordinate is xk plus 1, but the y coordinate is actually we have to choose, we have to decide among yk and yk minus 1, because the circle is actually coming down in this octant. The circle is actually has got a negative slope and y values keep reducing while x values keep increasing in this, for this particular octant. So, for the next x position, we have to choose whether we have to pick the yk position or the yk minus 1 position. So, how do we pick whether the next y coordinate is yk or yk minus 1, so that we can plot this or this, is based on the midpoint, is based on the position of the midpoint relative to the circle boundary. So, what is the midpoint here? For the possible y positions, exactly choose the middle position. So, this position is the midpoint. So, what is the principle behind this midpoint procedure is, if the midpoint for the two possible pixel positions lies inside the circle boundary, that means the circle boundary is close to the upper pixel. Try to understand this. Let me repeat that again. If the midpoint happens to lie inside the circle boundary is close to the upper pixel, that means here in this case we will be choosing the yk. If the midpoint is outside the circle boundary is close to the inner pixel, that is the lower pixel, that is yk minus 1. So, that is how we take our decision. So, based on the position of the midpoint with respect to the circle boundary. Now, how do we know where the midpoint is with respect to circle boundary? So, take the coordinates of the midpoint and substitute them in the equation x squared plus y squared minus r squared. So, compute the midpoint coordinates, substitute the x value and y value of the midpoint in the equation x squared plus y squared minus r squared, and see if it is equal to 0 or less than 0 or greater than 0. So, that is how you can know the position of the midpoint. So, let the midpoint coordinates be, the x coordinate is known for the midpoint, which is xk plus 1. The y coordinate is yk plus yk minus 1 by 2. So, it is actually like from yk to yk minus 1 we are going, it is yk minus half. So, it is yk minus 1, the midpoint is exactly at xk plus 1 comma yk minus half. So, what is the next step? Take these midpoint coordinates, put it in the equation x squared plus y squared minus r squared, and then check if it is equal to 0 or less than 0 and greater than 0. So, that is how our decision parameter starts. So, let us take the derivation here. Let p k be x k plus 1 whole square. This is x squared plus y squared minus r squared. So, now we have to check whether p k less than 0, p k greater than 0 or p k is equal to 0. What does p k less than 0 indicate? That this midpoint is inside the circle boundary. So, when the midpoint is inside the circle boundary, choose the upper pixel, that is y k. If p k greater than 0, the midpoint is outside the circle boundary, then choose the lower pixel. So, that means the next y is y k minus 1. So, if we start our derivation, p k is this and take p k plus 1. So, wherever there is k, replace that with k plus 1 for the next decision parameter, because always we do this because we want a relationship between the current decision parameter and the previous decision parameter, because to have recursive equations. So, recursive equations are faster in computation. So, the next decision parameter is wherever there is k, replace that with k plus 1. So, in this equation k, replace that with k plus 1, k here k plus 1. So, we have taken this, and the next step is to take the difference between the two decision parameters, p k plus 1 minus p k, which is 2 x k plus 1 plus y k plus 1 minus half whole squared minus y k minus half whole squared, because this difference is important so that we can take p k on to the right. So, you can sit and take these steps and you can follow, derive them. It will get simplified further. You can keep these slides, observe them carefully. The next decision parameter is p k plus 2 x k plus 1. Take the p k on to the right. So, next decision parameter is equal to previous decision parameter plus 2 x k plus 1 plus y k plus 1 minus half whole squared minus y k minus half whole squared. So, observe this k plus 1 all in the suffix, observe k plus 1 all in the suffix for y, indicating next x and next y. The next x is always 1 higher than the previous x, because we are going to sample the circle along x axis at unit intervals. So, next y is either y k or y k minus 1, it depends on the sign of p k again. So, case 1, if p k less than 0, that means the midpoint is inside the circle boundary and the circle boundary is close to the upper pixel. So, next y is y k. So, that is what is mentioned here. The next pixel that we will be plotting is x k plus 1 comma y k. So, that is the next y is y k. So, in this relation for p k plus 1, replace the next y with y k. So, y k minus half whole squared minus y k minus half whole squared reduced to this becomes 0, and you are left out with the term p k plus 2 x k plus 1 plus 1. So, the case 2, if you come to p k greater than or equal to 0. So, first we have considered the case 1, p k less than 0, that means the midpoint is inside. Now, for case 2, p k is greater than 0, the midpoint is outside the circle boundary. Now, then the y we will be choosing is the lower pixel or the inner pixel, which is y k minus 1. So, the next pixel to be plotted is x k plus 1 comma y k minus 1, and replace y k plus 1 with y k minus 1 in the equation for p k plus 1. You get this relation, this expression on the right. This expression can be simplified like this. Observe this expression carefully, y k minus 1 minus half whole squared minus y k minus half whole squared. This term remains as it is, but this term becomes y k minus 1 minus half whole squared minus y k minus half whole squared. You can slightly rearrange this term like this as shown in the next equation, subsequent equation. Y k minus 1 minus half can be conveniently written as y k minus half minus 1. Just a little rearrangement of terms, y k minus 1 minus half can be written as y k minus half minus 1, and put a bracket for y k minus half, treat that as a and this as b. So, a minus b whole squared like. So, you can conveniently cancel out this a square and here a squared term. So, for that we have simplified this. So, p k plus 1 is equal to p k plus 2 x k plus 1 plus 1 plus 1 minus 2 times y k minus half. This a squared term get cancelled, and you are left out with b squared, that is 1 minus 2 times y k minus half minus 2 a b. So, we have done a little simplification here. It is you can easily understand this. This part of the equation does not get altered, does not get simplified further, while this gets simplified like this, 1 minus 2 y k plus 1. If you take this 2 inside and multiply, 1 minus 2 y k plus 1, 2 minus 2 y k and 2 minus 2 y k, take the minus 2 out and you get this y k minus 1, minus 2 common and you get y k minus 1. We did this intentionally to say that the next y is y k minus 1. So, the next addition parameter is actually p k plus 2 x k plus 1 minus 2 y k plus 1, all in the suffix, indicating that the next y is y k minus 1, all in the suffix here k plus 1, indicating that the next x is previous x plus 1. So, as we did in the Bresenham's line drawing procedure, the decision parameter, the initial decision parameter is always to be computed to start with. So, take p k as this equation as we started with this, wherever there is k, replace that with 0, and p 0 is equal to x 0 plus 1 whole squared plus y 0 minus half whole squared minus r squared, and the initial point x naught y naught is equal to 0 comma r. As you know, a circle with center at origin and has a radius of r units, we started with the first point 0 comma r, and we will have to proceed till the x and y coordinates satisfy the relation x is less than or equal to y. You will understand this much better when we solve a simple problem based on this. And the first decision parameter, that is p naught, the initial decision parameter is given by x naught is 0, y naught is r. So, 0 plus 1 whole squared, 1 plus r minus half whole squared minus r squared. If you reduce this, expand this, a minus b whole squared, r minus half whole squared using a minus b whole squared formula. So, you get 1 plus 1 by 4 minus r, which is 5 by 4 minus r. But 5 by 4 is a fraction, and it is approximately, you can round it off to 1 minus r, because for all our examples r will be considered as an integer, and so we have approximated this 5 by 4 to be an integer as 1. So, based on this, if we solve a simple problem here, let us take a circle with center at 5 comma 5 and radius of 8 units. So, we solved we did the derivation or the steps using a circle with center at origin, but now if given a circle with center somewhere else, say 5 comma 5 as given in this problem, what is that you do is assume that the circle is at origin and then compute all the x and y points and then add this center to every point that you compute. So, that means using this center, whatever points that you compute, or using origin you compute the points and then add to every point the 5 comma 5, because that is the center, that is the actual center of the circle. So, to start with, first compute p naught is 1 minus r is 8. So, p naught is negative. So, tabulate the values for k, p k, x k plus 1, y k plus 1, and the actual x k plus 1, y k plus 1, as I said, with center at other than origin, you will be adding the center to every point that you compute. Okay. So, if p naught is minus 7, that means p naught is negative, p naught indicates that p k indicates that it is actually the decision parameter, and if we get a negative value, it indicates that the midpoint is inside the circle boundary and we will be choosing the upper position. Okay. So, midpoint is inside the circle boundary, that means for the y values you take the same. So, 0 comma 8 is the first point on that octant. Okay. So, 0 comma 8 and the first x value, next x value is 1, next x value is 2, 3, 4, 5, 6, you can keep going, you can till, but you do not know exactly where to stop, wait for computing for the y values. You can compare x and y values whenever x gets bigger than the y, or x is less, as long as x is less than or equal to y, you can compute. Okay. So, if you use as we did in the previous Bresenham's case, the first decision parameter is minus 7 negative. So, x value is 6 while x value is 1, while the next y value is same as previous. For P1 case, so you use the equation for next decision parameter, which is in this case, that is Pk plus 1 is equal to Pk plus 2xk plus 1 plus 1, where xk plus 1 is the next x value. So, if you the next x value, which is 1. So, 2 into 1 1 plus 1 minus 7 plus 2 plus 1, which is minus 4. So, that is minus 4 x gets incremented by 1, while y, because this is Pk is negative, y is same as previous. So, that is how, if we keep going, what we get is the points on the circle like 1 8 2 8 3 7 4 7 5 6 and C 6 5. So, 5 6 is actually a point where x is less than y, while 6 5 is a point where x is greater than y. That means, we are actually flipping or switching from from that octant to the next octant. So, what is that we do finally is this is where you can stop. The stopping condition is has arrived because x is greater than y. So, we will be taking this as our last point on that octant. So, 5 comma 6 is the last point on that octant, and here add that 5 5 center to every point that you compute here. So, 1 plus 5 8 plus 5, 2 plus 5 8 plus 5. So, 3 plus 5 7 plus 5. So, when you add center to the points that we computed here, you get the actual points on that octant. So, that is how we can solve a simple problem. To summarize, the midpoint circle drawing procedure is more efficient, and it uses the concept of octant symmetry, because circles exhibit the property of octant symmetry. It is just enough that we compute points on one of the octants. For our interest, we have chosen the octant that is the left octant in the first quadrant. So, in the first quadrant there are 2 octants. So, the upper octant. So, in that the circle has a shape where the slopes are gradually they are actually negative slopes. So, from 0 to negative, the circle slope moves from 0 to negative. So, as x increases, we are going to sample the a circle along x axis at unit steps, and y's are calculated, while y values keep decreasing, x values keep increasing. So, this procedure is more efficient and simpler. If we calculate one point on one of the octants, the remaining 7 points on the remaining 7 octants, symmetric octants, can be easily plotted by interchanging the computed values and by changing the signs. Okay. So, that is how we have learned this today in this session, the midpoint circle drawing procedure. We have also worked out a problem, and that gives us more clarity on this procedure. So, hope you will implement this in a program, and you can try working out more problems, taking more other radii, other values for the circle, other centers, and try solving a simple problem. Okay. So, thank you for being there, and thank you.